not here. So Stavros, take it away.
Thank you very much. I wish to thank the Newton Institute, Ulrike Tillman and Ricardo Chapa for their invitation to speak. And I hope that I can visit someday in person. Right. So let's start. I have three parts that I want to talk about, and I will try not to be too technical. The point is to make contact with an area called quantum topology, which is a relatively new area in mathematical physics, and the analytic ideas of resurgence or special functions and their analytic continuation properties. So quantum invariants of three-dimensional objects, they come in three realizations, at least that I know of. One of them are functions defined on complex roots of unity, so only on the unit circle, but only at the complex roots of unity, and they are complex valued. Those functions are typically not even continuous. The second realization is a Q series with integer coefficients. That means formal power series in a variable called Q with integer coefficients. Typically, these formal power series are analytic inside the unit disk. Or they come as asymptotic series, and these are the usually known factorially divergent formal power series. And by three-dimensional objects, I basically mean three-dimensional manifolds, closed or with boundary. With boundary, the simplest examples and interest to us would be the complements of a knot in the three-sphere, in which case the boundary is just a torus, two-dimensional torus. So 15 years ago, in a paper called Chen-Simon's Theory, Analytic Continuation and Arithmetic, I explained how to pass from one of these realizations to another and formulated some precise but numerically testable and numerically testable conjectures called resurgence conjectures about these objects. And I also gave examples that one can test the theory, examples that are interesting both geometrically and are non-trivial analytically. So what these conjectures imply, those packet of resurgence conjectures, what they imply and refine actually to all orders in perturbation theory and with exponentially small terms included, they imply Kashaev's volume conjecture. I will not even state it, but I want to tell you that this volume conjecture of Kashaev relates the Jones polynomial of a knot and its parallels to Thurston's hyperbolic geometry, that is to the hyperbolic volume of the knot complement. That is to lead in order. And another conjecture that they also imply is Witten's asymptotic expansion of his invariant, the Witten-Reshetikhin-Turaev invariant of a closed three-manifold. Okay, I'm not expecting that people know what closed three-manifolds are or what quantum invariants are. I do want to say one thing, that in the upcoming thesis of Campbell Wheeler, a graduate student at Max Planck, that Don Zagier and I are co-supervising, it concerns these conjectures for closed hyperbolic manifolds. In particular, an interesting test case is the manifold obtained by half surgery on the figure-8 knot. Figure-8 is the simplest hyperbolic knot. Half a surgery is a closed hyperbolic manifold with the homology of the three-sphere. And there's a lot to say about these invariants. So these factorially divergent series, they do not come from solutions of difference or differential equations. In that sense, the resurgence origin is a little unclear, but they do happen to have a resurgence structure. But although there is no differential equation, there is usually an underlying linear Q-difference equation. And the reason for this, it's actually very simple. These invariants are typically Q hypergeometric sums, and the latter are always Q-holonomic by the fundamental theorem of Zeilberger's theory. So in particular, Q-difference equations, linear Q-difference equations emerge and are satisfied for the Color-Jones polynomial and other quantum objects. That's what Tangle and myself observed some time ago as a trivial consequence of Zeilberger's theory. There is another feature of these factorial divergence series, and this is an arithmetic feature. I visited Jean et al. In Orsay in 2006 and 2007, where I told him about these conjectures and the dual aspect of resurgence and arithmetic. He was a little surprised about the resurgence, given that it was new to him. But as far as the arithmetic goes, he had no comment. All right. So typically by arithmetic, I will give examples, of course, but I mean that the coefficients of these factorial divergence series are elements of a number field. For example, the trace field of a hyperbolic knot. All right. So now let me come to the second part, which is some numerical discoveries. Yeah, maybe I'm going too fast, but okay. All right. So that was a kind of background of some general comments about power series in quantum topology. So I want to talk about some recent work that involves numerical discoveries for some interesting quantum invariants of knots. This is joint work with Campbell Wheeler. You can see it on the archive. It concerns two invariants that I want to focus on. The first of which is the 3D index of three physicists, mathematical physicists, Dimofte, Gaiotto, and Gukov. So what is it? It is actually a collection of formal power series in Q. Now, technically, the powers of Q are either all integer or all half integer. Finitely many negative powers of Q and arbitrarily many positive power. That's why I put this parenthesis here. I mean, so it's a Lorent, formal Lorent series with integer coefficients. So for every manifold M with torus boundary, there is a collection of such series, and they are parametrized by two integers M and E. These two integers are labeling a homology class of the boundary of the manifold being a torus. The M and the E do not usually stand for meridian and longitude, which is the usual way to parameterize the homology of the boundary, but instead they stand for magnetic and electric, because this 3D index is actually part of some magnetic electric duality. Okay, so this collection of Q series is defined as a state sum using an ideal triangulation of the manifold. So we take a manifold, we triangulate it, but we triangulate it not using usual tetrahedra, as topologists do, but ideal tetrahedra, as Thurston first did. And then to each ideal tetrahedron, there is a building block, which is the tetrahedron index. It also depends on two variables, M and E, the very same kind of variables that you see before. And it has a formula as a sum. So it's a sum where you sum from somewhere to infinity of this -1 to the n times q to a quadratic form. This is a quadratic form in the variables m, e, as well as n, the summation variable. And the denominator is the product of two quantum factorials. So this q semicolon q sub n is the product of 1 minus q squared, 1 minus q to the n. If n is greater than or equal to 0, it satisfies a first order linear q difference equation. What happens when n is negative? If you actually try to solve the equation backwards because it has a wall, it's not a monic equation, you find out that the infinite, the Pochhammer symbol when n is -1 has to be infinity. That's actually good news because the Pochhammer symbols are in the denominator. So rather than summing over a truncated lattice, you know, from minus e comma 0 to infinity, you can in fact sum over all integers, with understanding that the denominator makes the sum vanish if the Pochhammer symbol is negative. So the building block is a tetrahedron index where we're actually summing a q-hypergeometric function and we're summing it over a lattice. Now, when you sum over a lattice, for instance, when you sum the function q to the n square, where n goes from -infinity to infinity, you get a perfectly fine q series. But when you try to sum over a lattice, the function q to the n, when n goes from -infinity to infinity, you find out that this actually does not make sense. Because the way we're summing here, by summing, I mean that I'm talking about convergence. So for every fixed power of q, only finitely many terms in the sum contribute. Okay, and that is not the case when you try to sum q to the n from -infinity to infinity. So because we're going to be summing over the lattice, this will cause issues with convergence. Okay, so these are the building blocks of the theory. And using, for instance, the ideal triangulation of the figure 8 knot, the simplest hyperbolic knot, using two ideal tetrahedra. I did not draw the triangulation. It doesn't really convey a lot of information, but if I had drawn the triangulation and if I put integer variables at each edge of the triangulation, and then I contracted, I put two copies of the building block and I contracted indices according to the phase pairings of the triangulation. If I had done that, you would find out that the DGG index at integers m comma e is a one-dimensional sum over integers of the product of two building blocks because we have two ideal tetrahedra. The building blocks are evaluated at some linear forms that depend on the summation index as well as m and e. And I also have some quadratic, actually not quadratic, linear dependence on the summation variable. And although these building blocks may involve negative powers of q, the claim is that this sum is in fact convergent and makes a convergent q series. Okay, so this is just an example of the 3D index. You may wonder, in fact, why is this called an index, and what does that have to do with physics? So I will say just a few words, and maybe please correct me if I'm naive. So basically, this is an index, as in the Atiyah index theorem, and it counts BDS states. Hence, we get integer coefficients not rational numbers, which appear in enumerative problems, for instance. Here we get integers of some n equals 2 superconformal field theory in 6 dimensions, compactified in 3 to make a theory on R3, compactified along a 3 manifold. Okay, and then there is some correspondence along such theories which allow you, in some cases, to compute them exactly and get cut and paste formulas like the one that I was discussing here with the building block. So that's all nice. In particular, every integer that you get, I mean, the power of q to the 10 in this invariant is apparently some topological invariant of the figure 8 node complement, and it counts some cohomology of some space yet to be defined mathematically. Now, the topological invariance of this 3D index is a little tricky. By topological invariance, I mean the fact we need to prove that this invariant is independent of the ideal triangulation chosen. And it is true that ideal triangulations are connected by Pachner moves, where you decompose 2 tetrahedra into 3. I'm sorry I did not draw the picture. So it is known that, first of all, every 3 manifold with torus boundary can be ideally triangulated, and second, the set of such triangulations is connected by Pachner moves. The problem, however, is that the triangulations for which you can define the 3D index by formulas of this kind are not all, but they are the ones that they satisfy some non-degeneracy conditions. For instance, if the triangulation had a strict angle structure, which is some necessary condition for hyperbolicity, then the sum converges. But in general, the sum converges if and only if the triangulation has an index structure, which is a dual to some angle structure condition. Now, in the subset of triangulations with an index structure, that subset is not known to be connected under Pachner moves. And because of that, you have to work a little harder to prove topological invariance. This topological invariance was proven in a paper with Craig Hodgson, Chaim Rubinstein, and Henry Segerman at a cost. The cost was that we had to deal with hyperbolic knots or cusp hyperbolic manifolds, but not, for instance, the complement of the trefoil. There was an alternative approach to the 3D index, which was given in some work with Rinat Kashaev, in which case the 3 variables here, the 2 integer variables and the q variable, become a modular variable. Q is e to the 2 pi I tau, tau in the upper half plane, and 2 Jacobi variables. And in this case, topological invariance is more manifest. So below, we will be using what I call the meromorphic 3D index. And in fact, we will specialize it when the Jacobi variables are 0. So the 2 integers you see here, L and L prime, are 0. So that's one kind of topological invariant. In other words, it's going to be a Q series with integer coefficients, which is the meromorphic 3D index when L and L prime is 0. That's one. By the way, I should say that these are Q series with integer coefficients, which are analytic inside the unit disk, the Q unit disk. But they are also analytic outside the unit disk, except that they are defined by one formula inside and one outside, which is a little bit, this is not so standard, because usually you think of the unit disk as a natural boundary. Yet these analytic functions are actually defined as functions of tau. They are defined both on the upper and on the lower half plane. In other words, they're defined on the complex number minus the real numbers. Okay, the second invariant of a knot is what's called the Turaev Viro invariant. And it is defined using the ideas of quantum field theory as go back to Witten and Jones and Reshetik in Turaev. So basically to a knot K, there is something called the Color-Jones polynomial. So it's a sequence of polynomials, J sub K for the knot and K for the index, the spin of the corresponding representation. So you take, you fix a positive integer m, and then you take the first m Color-Jones polynomials. You evaluate them at that root of unity, which is actually m plus a half. It's been shifted to make exponential growth, and you take absolute value square, and then you multiply by some constant. Essentially, I did not write down what this is. It's basically sine of pi k over m plus a half. And you use a normalization factor, and that is an invariant of a knot. It's a variation of the classical Turaev Viro invariant, where we have shifted the integers m by a half to cause exponential growth. So there was a conjecture by Chen and Yang about the growth rate. So a volume conjecture about the growth rate of this Turaev Viro invariant, which was a different version of Kashaev's volume conjecture. Okay, so our first experiment with Campbell was actually to compute the first few terms in the asymptotic expansion of the meromorphic index. So, as I said, the meromorphic index is a power series with integer coefficients. So here is the first few of them. Okay. What can you see? Well, first you can see that the numbers are kind of, they have mixed signs. They have positive and negative signs. So they're not kind of numbers you see if you do partitions. They do grow. But in fact, these numbers, the exponential growth rate of these numbers is like partitions. So the coefficient of q to the n is basically exponential of a constant times square root of n, just like partitions. Okay, so this is a function, an analytic function inside the unit disk, and we want to compute radial asymptotics. Radial asymptotics means what happens when q goes to 1. So when q equals 1, you have to sum, 1 minus 4 minus 1 plus 36 plus 70 plus 100 and so on. Of course, this sum is nonsense. It's a sum of integers that is not stabilizing. And basically what this means is that this radial asymptotics of this function grows exponentially. So if we set q to be equal to the 2 pi a tau, and tau goes to 0 nearly horizontally. So nearly horizontally, it means it will, if we can fix the argument to be, let's say, 0.1, That's a good number as far as figure 8 goes. And then, you know, let the magnitude of tau go to 0. And on that ray, we found out the following. I'm just reporting experimental results here, and I will, of course, tell you more about them. So what we find out is that, so as tau is small, first of all, the radial asymptotics blows up. It grows exponentially. And it grows exponentially at the rate of e to twice times the volume of the figure 8 divided by 2 pi times tau. Okay, what is the volume of the figure 8 knot complement? So hyperbolic geometry, according to Thurston, says that, in fact, the geometrization conjecture of Thurston, which he did prove for knot complements, says that typically a knot complement is a hyperbolic manifold, in which case, if it is hyperbolic, and it is for the figure 8, the hyperbolic structure, the complete finite volume hyperbolic metric is unique. That follows from most of rigidity. And but the manifold is not compact, so a priori it could have infinite volume, like Euclidean plane is a non-compact complete hyperbolic manifold of constant curvature 0 with infinite volume. However, in hyperbolic geometry, the volume is typically finite, and for the figure 8 knot, it's given by basically 2.029. It's basically 2.0, but it's really 2.02. And what it is, it's the imaginary part of twice the dilogarithm. So the dilogarithm of x is sum of x to the n over n square instead of over x to the n. And you evaluate it at the 6th root of unit t. And that is the volume. So the volume is the simplest invariant of a Riemannian manifold, of a hyperbolic manifold, and that volume is captured as the exponential growth rate of the asymptotic expansion, I mean, of the radial asymptotic of this particular Q series. Let me say that when I say we found out numerically. This is not a theorem, it is a conjecture. Let's move on a little bit. So after you get the exponential rate, then typically you find a power of tau to some fractional power of tau, very typically and always in case of algebraic geometry, where the monodrome is quasi-unipotent. There you find fractional powers of tau, which are rational numbers. In our case, the power of tau is tau to the minus a half. Very good. So we get that number too. And then the constant that comes out, the usual so-called Stokes constant, is a constant that typically is the most difficult part of the problem. In our case, the Stokes constant is 1 over 3 to the 3/4 times 1 over 2 to a quarter, to a half. And after you subtract, I mean, you remove these constants, then you find 1, and then the next term is minus 19 over 24. There is this factor root of 3 to the cube, root of minus 3 to the cube, times 2 pi I tau, and 1333 over 1152, you know, and so on and so forth. Okay, so I remembered the number 1333, you know. It's kind of a strange number. And I remember that it had appeared in some in the asymptotic expansion of the Turaev Viro figure 8 knot. I only had done that. I had done it to 10 orders, and then looking at the files, once you recognize that the 1333 agrees, that file with the 10 coefficients also agrees the next one, the 100. Well, the 1.6 million basically number. And then we checked this expansion of the meromorphic index to 10 orders, and they agreed, and therefore we had a conjecture. Now notice that the coefficients that we get here involve square root of -3. And what is square root of -3, or rather, what is the number field generated by the square root of -3? It is nothing but the trace field of the figure-8 knot. Okay, so the 6th root of unity that you see here is actually a generator of the trace field. And if you did that for the 5-2 knot as we do it, then you would find out that the coefficients here are numbers, algebraic numbers, but they belong on a cubic field. So, but I'm not going to give you the data for 5-2. Okay, so our explanation, therefore, I mean, our discovery explains the Chen-Yang volume conjecture. I will tell you more later about numerical asymptotics. It's a very interesting problem. I'm sure many of you actually know about this. People typically want to skip it, but I will say a few words. So the conjecture is the following. If you take any hyperbolic knot K, and you take this Q series, and you parameterize Q by e to the 2 pi I tau, and tau goes to 0 nearly horizontally, then it's asymptotic to all orders to the asymptotics of the Turaev Viro invariant as m go to infinity. That is the conjecture, which we do not have a proof of even for the case of the figure-8 knot. By the way, you can prove that the Turaev Viro invariant of the figure-8 knot has an asymptotic expansion of this form. That you can do because of positivity, positivity which is accidental in the Color-Jones polynomial of the figure-8 knot. So yes, you can prove the asymptotic expansion for the figure-8 of the TV invariant, but I don't know a rigorous method to prove this asymptotic expansion here. I should also say that the asymptotic expansion that you have here in the middle of this page involves a function, but this function does not really satisfy some linear Q-difference equation. So, although it has some other representations that maybe one can use to prove the existence of this expansion. So this conjecture says not only that the expansion exists, but the two are equal to each other to all orders. Okay. So I've done work with Don Zagier for about 12 years now, but one discovery that we did and we didn't realize at that time is that Q-Haber geometric series have asymptotics, radial asymptotics that depend on a sector. Now, everybody knows that asymptotics of entire functions, even solutions to linear differential equations with polynomial coefficients, they have asymptotics that depend on a sector because infinity is typically an essential singularity. So the Stokes phenomenon is obvious in the case of solutions to linear differential equations, but the Q series that I am discussing here is not a solution to a problem of a linear Q difference or differential equation. So it was a little bit of a surprise. Okay, so having known that, we decided to look at vertical asymptotics of the meromorphic index. Vertical means that tau is on the positive imaginary axis and goes to 0 vertically. Now, there's a huge difference. For instance, suppose that, tau has an argument which is nearly horizontal. For instance, if the argument of tau is 0.1 and the magnitude is 1/100, what would be the magnitude of q and what would be the magnitude of q tilde? You can compute, in this case, the magnitude of q and q tilde is about the same. On the other hand, when q is on the imaginary axis, the simplest point of the imaginary axis is actually tau equals I, in which case q tilde, which unfortunately I did not write, q tilde is e to the minus 2 pi I over tau, becomes e to the minus 2 pi. And that's about 0.01, about. Which means that if you're actually working on the positive imaginary axis, q tilde is very, very small, exponentially small, and that causes all kinds of issues with accuracy. You lose accuracy very quickly. In any case, we managed not to lose too much accuracy, and what we found with Campbell numerically is that if you approach 0 vertically, then you find three things. First, the answer as before is here, with e to the 2 times volume over 2 pi I. That is one answer. Now keep in mind here that because I is purely imaginary, this term, the exponential term, is now an oscillatory factor of tau. Okay, so it's a pure oscillatory. And for reasons of democracy, you expect it to see the complex conjugate of it, and we do see. Oh, by the way, these are Q series with integer coefficients. So when tau is on the purely imaginary axis, that means that Q is positive real. So Q is between 0 and 1, and therefore, if you evaluate this function, you find a real answer, and therefore it's radial asymptotics. When you go vertically, it's the radial asymptotics of a function which is real valued, so it has to be real valued, and therefore, since the first exponential is oscillatory, we'll have to have the complex conjugate. So yes, and the complex conjugate means you replace square root of minus 3 by minus root square root of minus 3. This is what you would expect to find as before, except that two new series appear. Okay? All right, they appear. So two new series and no more. So, and the first constant here that we were able to compute numerically is this one, 0.44582, and so on. By the way, when I say here that we have a power series as before, these power series, we know them exactly to about 100 coefficients. And these power series are conjectured to be Borel-summable. And in fact, this asymptotic expansion, if you did Borel resummation, actually median Borel resummation of this series, you expect to find here equalities after you put down certain exponentially small corrections, which are expressed in terms of the very same series B as before. So when I say here series, although I only write a few coefficients, we do have 100, and you can actually do numerical Borel resummation if you want. But for this new series, we got this number. And then, of course, based on everything I said before, we try to recognize this number. In terms of what? In terms of pi, square root of -3, you know, and things like that. But we failed. So then we doubled the precision and did the calculation. This time it took about a week to get twice as many digits as the ones that I wrote here. So we got more digits, but we failed again. By the way, it's an interesting problem, you know. I mean, for those of you who like to recognize numbers, Don Zagier is a champion on this, you know. You just give him a 40-digit number and yeah, well, he will recognize it for you. But he will not just recognize a number. If you gave him, you know, e plus pi, he would, of course, never recognize it. You have to give him some context. But the context here was number fields, and we failed. So then we had an idea to actually use a resummed version of our asymptotic series. Our asymptotic series depends on two variables. I've only written one variable here. And it is possible to actually resum them into basically series of rational functions. And after we did that, and we found out numerically the following thing. So consider this integral here, var pi, I think they call it in LaTeX, which is an integral over the reals of du over square root of this. What is this? This is a Lorent polynomial in e to the u. So it's a number. I mean, this number has a little bit of a problem because when u is the logarithm of golden ratio or its conjugate, so 3 plus or when u is equal to the logarithm of 3 plus or minus root 5 over 2, and these are both real numbers, then the integral has a little bit of an issue. You get a square root of branch singularity. The integral is still absolutely convergent, so you actually get out two complex numbers actually here. And if you add them up, you divide by pi, you get to all the 20 digits that I wrote an identity. Okay, so this identity here, which is conjectural, of course it is conjectural because the existence of this asymptotic expansion is conjectural. So I'm not going to be continuing talking about conjecture. So anyway, this numerical number was identified with this one and explained the failure of the previous recognition. Because what is this pi? It is actually a period of an elliptic curve defined over Q. And in fact, the elliptic curve is nothing but the a polynomial of the figure 8 knot. It is the defining polynomial of the SL2C character variety of the figure 8 knot complement, which is a topological invariant itself, which appears in hyperbolic geometry when you try to deform the complete hyperbolic structure, or when you try to explain the hyperbolic structure of Dehn fillings on the figure 8 knot. Okay, but in any case, I'm talking about an elliptic curve. I mean, 2 centuries ago, I guess in the 18th century, they were calling this an abelian integral of the second kind. Second kind means it's a meromorphic one form on a curve with 0 residue. First kind means holomorphic one form, but this is a meromorphic one with 0 residue, okay? Very good. So the number we came across was an abelian integral. And abelian integrals are examples of something called periods. This was the first word in the title of my talk. And what is periods? Well, a period is a multidimensional integral of a differential form in many variables and variables, which is rational. So in other words, you take, let's say, dx1 up to dxn, and you multiply it by a rational function of n variables, and you integrate it across a domain which is defined by some inequalities of a polynomial with rational coefficients. So since there are countably many rational numbers, there are countably many rational differential forms and countably many rational domains. So therefore, the script P set of periods is a countable subset of the complex numbers studied by Kontsevich and Zagier. It's not just a subset, it's a subring. It is not a field. It is not expected to be a field. But it is this subring which contains essentially all the numbers of interest to algebraic geometry. I give you an example. Pi is a period. Everybody knows it's the integral of dx wedge dy over x squared plus y squared less than or equal to 1, otherwise known as the area of the unit disk. Log 2 is also a period because it's just the integral of dx over x from 1 to 2. E, on the other hand, is not known to be a period, and conjecturally it is not a period. By the way, the volume of every hyperbolic knot complement is a period, and that is a theorem. Because the dilogarithm at algebraic values is a period, and the volume is a sum of linear combination of dilogarithm at algebraic numbers. Okay. What about the next constant? Well, the next constant here. So since we have, as I said, 100 terms of this series, we can subtract the series here from the function, twice subtract them, and now that we have an exact value is an integral, yes, but if you have a numerical integral, Paris can compute to 500 digits in seconds. So you subtract all of this, and now you can hope to compute the next coefficient. What was the next coefficient? The next coefficient numerically is this, 0.1105. Something. And following what we did before, this time it was actually easy to recognize this number. What it is an integral over some domain, essentially similar to the previous domain, of, well, before we were integrating, where is it here? The 1 over square root of a polynomial in exponentiated variables. It is the same polynomial. Oh, I made a mistake. It's the square root raised to the 7th power. Sorry, that's a huge typo. The denominator should be what you see, but raised to the 7th power. And the numerator is a numerator, another polynomial, okay? So that's the next constant. I will not bother you, but there is the constant after that, and after that, and after that, and we computed the first 10 constants, and we found out, we identified them with periods of this apolynomial curve. But there is a theorem that says that, you know, an elliptic curve has actually only 2 periods, essentially, which means that the 10 numbers that we found satisfy linear, they satisfy linear relations with rational coefficients, and we found those linear relations. I'm not going to tell you about the remaining 8 numbers because I want to stress what's happening, the structure. Okay, now here is another, in case you are bored by this, and in case you're searching for the theorem, I will give you one. It's about time. So in some joint but unpublished work, we're writing it up right now with Rinat Kashaev that actually has to do with invariance of three manifolds using local fields like p-adic numbers. So motivated by invariance of local fields, we found the following result. The number that I told you before, the kappa number, which is the period of this elliptic curve, is equal to 1 over 80 pi I times a single integral of the square of the beta function divided by cosine of pi z, I suppose, where beta of x and y is Euler's beta function. Okay, so this is an identity. You can check it numerically, and of course we did. But more than checking it numerically, we can prove it. In fact, Kontsevich and Zagir, I mean, they have a certain kind of meta theory that every identity among periods has to follow from basically motivic change of variables, except that this is not exactly an identity about periods. The left-hand side is truly a period. The right-hand side, as far as I know, and maybe I'm wrong, is not a period, because this integral here is not an integral of some kind of algebraic function, a multiple integral of an algebraic function. The cosine is not a problem, but the Euler beta function is kind of a problem. Okay, so we have a consequence of some work with Rinat is an identity like that, and similar identities for the remaining constants. So this identity, by the way, explains some formulas of Craig Hodgson and Andrew Kricker and Raphael Siejakowski. Okay, now let me say a few things about numerical computations. One of my favorite subjects. So how do you compute this Q series, this meromorphic 3D index of the figure 8? So what our starting point is that we use an expression of it in terms of colored holomorphic blocks. The expression says that we're doing a sum over integers like before, but now we have the product of two Q series. These are not building blocks like tetrahedron indices anymore. These Q series, each of these Q series is the following. So the first one, H upper 0, is basically the sum, a Q-hypergeometric sum, like so. And H upper 1 is basically the same sum, same prefactor, same thing here, but you multiply it by some basically Frobenius deformation of this summand. So these are Q harmonic numbers, and E1 of Q is the first Eisenstein series. So, but the point is that these are explicit formulas. So this convergence here, for instance, is quadratic in K. So if n is equal to 10, and you wanted the coefficient of Q to the 1000, you only have to actually sum about 10 terms, you know. So it is very fast using these formulas to get as many coefficients of this Q series as you want, as many coefficients of the meromorphic index as you want. Moreover, these two building blocks, the two colored holomorphic blocks, they satisfy an explicit linear Q difference equation. I only get its second order. The fact that it is second order is an accident. Don't focus on that, because for 5-2 it is third order, and in general it's high order. I only wrote for you one coefficient, but the other two coefficients are polynomials in Q and Q to the n, like the first one. So they're both solutions to the same Q difference equations. We take the product of two and we sum it over the integers. And that is our index. In addition to that, the product of these two, they satisfy a third order linear Q difference equation. You can see it in this in our paper. It's an equation 82. It takes about half a page in small print. And using this, you can do even better calculation of the coefficients of these Q series. However, even though you can compute the coefficient of Q to the 10,000, and I did not put it down because these are handwritten notes, I didn't want to put any tech on them. So it's very easy to do that. But even if you knew this Q series to 10,000 coefficients, these coefficients by themselves are not sufficient to compute the radial asymptotics as Q goes to 1. Because computing the radial asymptotics, I mean, the terms themselves are highly oscillatory. So for this, we have to go back to the Q hypergeometric formulas that I gave you for the two building blocks and numerically compute the terms in the formulas, evaluate the computations for a range of values of Q. For instance, if you go vertically, you go from I over 200 up to 300, and you compute to accuracy of about 500 digits. After you do that, you need to numerically extrapolate the answer to high precision, keeping your 500 digits using, for instance, the Richardson transform. And after having done that, you have to recognize the algebraic numbers that you get. And that's how we compute the asymptotic expansions that I was talking about. In the paper with Campbell, however, we have a theoretical way to compute these asymptotic series using WKB solutions to a difference equation, like this difference equation. And we implement it, and then the ones we find exact matching of our calculations, the theoretical calculations, with the numerical calculations. Doing the WKB on a linear Q difference equation is maybe, well, perhaps it is a theorem, perhaps it is a conjecture, I don't know. And actually for arbitrary order, that's not so clear to me. But the point was to expose the number theory and the asymptotics that emerge in these quantum invariants, and for the first time see numbers that are not algebraic, but in fact are periods of curves associated to the noted objects. This is my last slide. Thank you very much.
It's only a comment, so I don't know if other people want to ask. Hello, this is Nalini Joshi. I just had a comment about your discussion of periods that came in the segment about elliptic curves.
Yes.
I think you said that, for example, E can't be a period. I just wanted to clarify that perhaps that's for, perhaps you meant elliptic curves with rational coefficients, because
yes,
in general, in general, I mean, you would have a modulus parameter, for example, which could give rise to any period, and transcendental numbers included. So I just wanted to clarify that. Thank you.
Yes. I mean algebraic varieties over, well, number fields. Yes.
Hi, Stavros. Here is Ines Aniseto. I just want to ask a very, very dumb question, which is you've identified in many slides above, in your first time that you wrote your series, the Stokes constant, but in there, you actually have the original series. So I'm used to seeing the identification of the Stokes constants as coming from a large order behavior, and then it shows up the Stokes constant. But you're saying that the first coefficient of that series is already a Stokes constant. How can you tell?
Yeah. Maybe I should call them, well, the one loop expansion. Maybe I should call them the constant term in the asymptotic series. Well, the fourth root of 3 as a constant appears in many, asymptotic expansions related to the figure 8 knot. I'm not. What? Okay. Yeah, maybe I should just call it the constant term and not the Stokes constant. I think, yeah, in the series that I mentioned, let me find out here. Okay, so in this series, if you actually look at the large asymptotics of the coefficients, so there is this 3 to the 3/4, but the large asymptotic of these coefficients involves another 3, which is the Stokes constant you're referring to.
Sorry, I was just confused. I just wanted to understand better. Thank you.
Yeah.
Thank you.
Anyone else? All right. Thanks, Stavros. Hope to see you again in person sometime.
Thank you very much. Bye-bye.